Right, gents, week 6. Yeah. Some further work on complex numbers today. Okay. And once we're finished today, we've finished what we're going to do until we start revision, of course, on learning outcome 1, the algebra and the complex numbers. Next week, we move on to learning outcome 2 and 3 and 4, sorry, which are integral and differential calculus, the subject of paper 2. Right. After this week, you've done the paper 1 stuff, yeah. So what I'm going to do this week is, as a way of kind of a little bit of revision of some of the things we've done last week, we're going to look at addition and subtraction of the polar complex numbers, using the method I would expect you to do if you need to do that in the exam, by the way. And then we're going to look at solving some specific engineering problems for complex numbers, which will come in handy because we'll be doing that in science as well, certainly in my electrical. Similar problem, or at least one of them today. Also, as usual, I've put some extra questions for you in the book that you can. I've picked out ones that are suitable to the stuff that we've covered and what you might get questions on. And right at the end of your notes this week, I'll put a typical exam question on the sine wave thing that we done a week or 2 ago, the equation of a sine wave. So it's typical of one of the bigger 15-mark questions that you'll get in the exam. That's more about that. So, addition and subtraction of polar complex numbers can be done manually, but requires some tricky knowledge of geometry, sine and cosine rules. Okay. So what I'm proposing to do is that you convert, if you want to add to or subtract two polar numbers, use the method of converting them to rectangular form first. So what I would recommend that you do here, if we write these polar numbers like that, in your exam answers, use that to say convert to such and such in rectangular form. So we're going to add to that 5 angle minus 45 degrees. That converts to, and we're going to add to that minus 4 angle 120 degrees. To do 3 manually would require you, guys, before you start, to add those 2 together and get a resultant, and then do the whole process again to add that last one to the resultant of those 2. You couldn't really do it in one go. So that becomes very tricky. So this method with the modern calculator is much easier. So what you're going to do is end up with 3 complex numbers in rectangular form over here that you can then add together, if necessary, convert back to polar, get a final answer if that's what the which it wants you to evaluate this in polar form, so it's looking for a polar answer. Right. What I would say though is maximum of 2 transfers, so you're going here from polar to rectangular, adding them up and then transfer them back. Don't do any more backwards and forwards than that. You can avoid it. So every time you're going to round a little bit. Right guys, we got the answers to the conversion of those 3 numbers to rectangular form. Yeah. Right, so that's plus 1. I've got to put on the end there for. Okay. Rectangular form, yeah? So, middle part, back to right. 5 angle minus 45. Right. 5, 3, 5. Yeah. Yeah. Which is right for 45 degrees. Think about it. You're going 45 degrees, you're going to end up with these two sides of equal length always, aren't you? Yeah. So that's the 3.535 there. All right, that's negative, but you're going to have 3.535 there because the angle is 45 degrees, half the full 90. The two side lengths of that triangle, there and there, are always going to be the same for 45 degrees. Yep. Okay. And the last one, minus 4 angle 120 degrees. Minus 2 plus 3.464 J. Okay. Okay, no, well you need to put in minus 4. What if you put that in? Shift, and I'll summarise for the video. What's needed to be done here is convert the first two vectors to rectangular using your calculator. There, there. Add them two together to get a result. Convert the 4 angle 120 and then take it away. Need to be careful with this minus 4 because it gives a math error on the calculator if you try and do that conversion direct. So what we need to do is take away the vector 4 angle 120. I've learned something this morning because even though I didn't know that did that on the calculator. Okay. Once you've taken that off, convert that rectangular number back to polar. Generally, you're going to be looking for an answer that gives you the size of the vector and the angle it acts at rather than in rectangular form. Sometimes you want it in this form, and you're going to see an example of that in a minute when you want to get the resistance and the reactance out of an impedance, okay, for electric. But other than that, generally you're going to want an answer in polar form eventually. So, moving on, I don't want you to get too hung up on the electrical why, this and the electrical stuff, because we'll cover that in science. So, it's about the maths here, okay? When we're in science mode next semester, I'm going to be keeping on about understanding the underlying electrical science behind this, rather than the detail of the maths. You should also really be competent at maths. So there are a number of applications of complex numbers in science and engineering, in particular electrical alternating current theory uses can have problems that involve complex numbers and vectors, and in mechanical, some vector analysis, forces and things acting at different angles on a body and that type of thing. Two planar forces. We're going to do a couple of examples in electrical and perhaps one in the mechanical area to show you where you come across these in engineering. So, we'll be doing a question today that would be quite similar to what you might get in the exam if I choose to do this type of question in the exam. because I'm trying to create some variety so I don't take it off the stuff. Right? So in alternating current theory, we can have two basic series circuits. An RL series circuit, a resistor and an inductor. You should bear in mind that these situations only crop up if the applied current is an AC current with change in direction. So this theory does not apply to DC circuits with batteries in them. Okay? So what we get with the RL circuit is an impedance Z that is a combination of what is the resistance of the circuit and another quantity called XL, the inductive reactance of the circuit. Okay? And XL is the unreal, the J part, if you like, and that's positive in an inductor. And R is the horizontal real part. They combine together to make the impedance Z at an angle theta in the middle. Right? So AC impedance is like the AC resistance of a circuit. Resistance is a DC term, still comes up, and all of these are measured in ohms. Every single one of them. But the Z is complex. It's got magnitude and angle. If we have the RC circuit, this is RL, resistor, inductor. This is RC, resistor, capacitor. The capacitor has a negative XC about it, also measured in ohms, the capacitive reactance. And it also has its resistance, and then it ends up with an impedance that is a combination of those two. Got magnitude and direction. Z at angle. This is Z ohms at angle theta. Okay? They're all in ohms. Everything there, all Z, R, and XL, and XC, all have units of ohms. Z is a combination of, Z is the polar number, or a rectangular number. It's a combination of the other two things. Okay? I wouldn't get too hung up at the moment on exactly what these are electrically, because we're in maths mode. So you're going to be given any electrical information that you need. Right? The second part I want to cover about that is what we also get is, with these type of circuits, we get current and voltage out of phase with each other. Okay? So in these two circuits, the current I is the same in both components, and that's along here. There's I. There's I. Okay? What we get here is we get a voltage across the resistor that is in phase with the current, got the same angle. For the inductor, we get a voltage across the inductor that is 90 degrees ahead of the current and the voltage across the resistance. The overall voltage, this one, is there, and that's got an angle about it. Yep. Over here, we've got a similar thing. This is VR along the horizontal. This is VC, 90 degrees out of phase in the opposite direction. They're completely 180 degrees out of phase with VL. The negative J term when we look at our complex number. And then we get V at angle 9 there. Again, these angles could be expressed in either radians or degrees. Okay. But VR isn't a rectangular number, it's a plane. The magnitude of that voltage is plane. The angle situation comes out from being out of phase with each other. I don't want to go into this too much, but what you've got here, if we take just that circuit, if that's VR, what we've got is VL is 90 degrees out of phase with it and ahead. So VR peaks 90 degrees ahead. So VL peaks 90 degrees ahead of VR. They're not peaking at the same time. So when you combine the two, you get the resultant voltage that's somewhere between them. The angle is somewhere between them. So the resultant or the applied voltage is in there somewhere. More about that in science. I really don't want to get too hung up on that detail, but it's important for this module that you do actually solve some typical engineering problems in the exam. You'll be given all the information you need in the form that you need it. Okay, so just trying to show where the problem comes from before we have a go at it. All right. So let's have a look at these problems here. Is that determine the resistance in series inductance or capacitance for each of the following impedances, assuming the frequency of 50 hertz. Okay, so you've got some extra information there. We're going to need to know why you've got. First of all, we've got A, where Z is equal to 4 plus 7J ohms. Let's draw a little diagram. Going 4 in that direction. Going 7 up there. So that's that. That green vector there, 4 plus 7J ohms. You all agree and understand that? From the last slide, what is the horizontal component of a impedance? What value to the circuit is it? No, forget voltage at the moment. We've got no voltage yet. We're just on impedance. You ought to go back 2 slides to the impedance one. The horizontal bit is R. This bit is inductive reactance vector. Okay. So the question says determine the resistance. So what is the resistance of this circuit? So R is equal to 4 ohms because that's that bit. Yeah. Now, XL is equal to what? 7 units. So, yeah. So why are we being given this frequency? It's been given the frequency because the value of XL is frequency dependent. Okay? I'm going to write separately over here, XL is equal to 2 pi times F. So therefore, hang on, 2 pi FL. Therefore, L, the question's asking for the inductance or capacitance. Rearranging that formula, XL over 2 pi F push the button. Please. .022 Henrys. Inductance is measured in, yeah. Or we could write that as 22 milliamps. Right. Now, the other two, B says you've got an impedance of minus 20 j-ohm. Look back at the diagrams on the impedance page. What does it mean if you've got just minus 20 j? Think of as 0 minus 20 j if you like. What type of circuit would it be to start? We've got a vector like this. Here's our diagram. Right, and our vector is none across either direction, just 20 down there. But what type of circuit is it? Looking back, it's an AC circuit, has to be, but what does negative J mean in terms of impedance? What's the component in that circuit? Now, what type of components in the circuit? Inductor or capacitor? The capacitor circuit. And that hasn't got any resistance because there's no R part to it. We'll deal with it the same. So there is no resistance. It's V here is a number that is 0 minus 20 j ohms. Therefore, R is equal to nothing. There is no resistance. It's not possible to build that circuit, ever. XC, the magnitude of XC, 20, isn't it? Size of it. So the capacitance, right? The other formula you need now is the equivalent of that one. Yeah, you'll get given these. You're not expected to remember them, not in maths. Okay. XC is also equal to 1 over 2 pi F times C. So you can find the capacitance by rearranging that formula. Look at the two. XC is 1 over. XL is just multiplied by. What that means in the circuit is if the frequency changes, one of those values goes up, the other one goes down. because they're opposites of each other. If we put frequency up, XC must get smaller. If we put frequency up there, XL gets bigger. So these two phenomena work against each other. More about that in science. So summing that last part up for the video then, what we've got there is we've had, because that's given to us in polar form, we've had to convert it to rectangular. That gives us the real part here that is the resistance, 7.5 ohms. The imaginary part there that is 12.99 ohms, XC. Okay. The negative sign tells us that's a capacitor and not an inductor. Once you move into science, you'll find to be a little bit more careful than that, because you can have a circuit that's got both an inductor and a capacitor in it, and overall the impedances could be either negative reactance or positive reactance, depending on which component has got the biggest influence of the circuit. More about that in semester 2. Okay, but for here, for this, you're not going to be given that kind of question. We then take that number without the sign into there, because the sign's just established as a capacitor. Use that formula, find the capacitance from the capacitive reactance. You then need, if you've got a positive XL, then you need to go into that formula to find the inductance. Right. Now we'll have a look at a slightly different type of electrode. An alternating voltage of 240 volts 50 hertz connected across an impedance of 60 minus j ohms. So let's draw this circuit. There's an AC voltage. There's an impedance drawn like a resistor. Z is equal to 60 minus 100J. Okay. The voltage is 240 volts. Right? If no angle is given, right, assumption is 0 degrees. Determine I, the resistance. Where does that come from in this question? It comes straight from there. Because that is in R minus XC J form. Yeah. This bit is the resistance. That bit is the negative XC. That's telling you as a capacitive circuit, because it's asking you to find that. So, from that, how do we find C? What can we get from that? What information will help us find the XC is equal to minus 100 ohms. The magnitude of it is 100. That's magnitude. Right, remember I told you that last time. If you just talk about the magnitude, that's how you define it. The fact that it's negative means that's a capacitor. Right? What this is, in this box here, right, in that resistor box, what it actually is, inside that box, there's a resistor in series with the capacitor. It's got some resistance and it's got some capacitance. Yep. Okay, but we just got it as a black box with an impedance of 60 minus 100 j ohm. That's what it is. Black box consisting of a series resistor and a capacitor. XC is 100 ohms. How do I find C? Hertz. 1 over 2 pi F C. The more times you write these things down, the more likely you are to remember them. Not even need me to give you it. One over 2 pi times 50 times 100. C equals 31.83 . So, the part C says magnitude of impedance. Tell me what to do to draw a little phasor diagram of those two impedance components. The 60 ohms with a resistor and the minus 100 j ohms for the inductive reactance. What do I draw? In fact, come draw it. The phasor diagram for 60 minus 100 j. Let's draw that in a different colour for you. Which one of these lines does represent a minus j? We pick the rubber up now. Where would you draw the line to represent the 60? Touch this. Draw on it with your pen. Get rid of that. Wrong. Zero degree. Sum that whole question up for the video. We've got 240 volts at angle 0. At 50 hertz applied to an impedance that has been given in rectangular form. We've taken out of that 60 ohms for resistance there. We've taken out to minus the 100 as the magnitude of XC there. Used it in this formula. You know, because it's negative, that it must be a capacitor, so we choose that version of the formula, put the numbers in, find out what the capacitance is. In terms of finding the magnitude of the impedance, that comes from a horizontal component, vertical component, negative in this case. We parallelogram those up, and then we use Pythagoras theorem to find the magnitude of the impedance, 116 ohms. And then we use the tangent, opposite side over adjacent side, to find the angle associated with the impedance. And the last thing, to find the current, we use Ohm's law with the full complex values of voltage and impedance to find the current flowing in the circuit and its phase angle relative to voltage. So it's just, the maths is about using the complex numbers, but we're trying also to put it in an engineering context. So, for the parallel circuit shown, figure, determine the value of the current I and its phase relative to the 240 volt supply using complex numbers. Alright, now what you want to know is you've got a parallel circuit here and you've got series as well. So how can I represent those two together as a complex number? Yeah, add components in series. But what has to go with this XC? Fully describe it in terms of its and capacitance combined. So that bit, right up there, is 12 minus 5J ohms. Yeah, right. We can use that bit together. That's one complex number. What about this? That's just resistor equal to 10 ohms for no J part. What we can say we got now, okay, impedance wise, an impedance of 10 in parallel with an impedance of 12 minus 5J. We've added those two components together that are in series. Yeah. Impedance as the AC opposition as well. But you're going too much into science with it, Lewis. What you've got is you've now got two complex numbers in rectangular form that you need to use. Take it from the question. Okay. If you're going to find the current, I, we need to be able to divide the voltage by the total impedance of the circuit. Okay. Now ZT here, I'm going to give you another formula you need to use. It's equal to, we call that value Z1, and that value Z2 is equal to Z1 times Z2 over Z1 plus Z2. So now do your complex arithmetic with those two values in that formula find the total impedance in rectangular form. If this is your new plan of action, find ZT in rectangular form. Convert, polar, use Ohm's law. Fine. No. If your voltage is in polar form, 240 volts, 50 hertz angle. So I'm going to pause that video there.